Hello everyone, I'm going to present a protocol OrgAn which can provide anonymity for an organizational network. This is a joint work with Easwar, Vivek, Mangipudi and Aniket. Suppose Jim, Pam, Ryan and Andy are part of a local area network and they want to access the internet through the relay or gateway of the local area network or some local services, and they don't want to reveal to anyone who is accessing what. For this talk, we'll focus on the outgoing traffic. So we'll protect the anonymity of the senders. We'll focus on sender anonymity. However, for anonymity, they don't want to rely on the relay or the gateway because all the traffic going through the relay or gateway can be observed by the office manager, Mike. Also, some of the users might be agents of Mike, and that's why they don't want to rely on each other for anonymity. And that's why we want a non-interactive protocol. Additionally, we want to achieve low latency to support many latency sensitive applications. So how do we achieve that? You can suggest to use Tor or mixnets. However, Tor or mixnets will reroute the traffic through multiple servers spread across the globe. And that might introduce a lot of overhead, as well as even for accessing local services, the traffic will be rerouted through the internet. That might expose the system to external attacks. So ideally, we want solution that can be deployed within the local area network. And for that, DCNet seems to be a good candidate. Let's see if existing DCNets can solve this problem. There are P2P DCNets where users interact with each other to achieve anonymity. This interaction can introduce a lot of overhead, and so the protocol can be slow, as well as you need to interact with each other. That's why this doesn't seem to be a good solution. There are solutions where interactions among the users are replaced by interactions among several multi-party computation servers. However, MPC itself adds a lot of overhead, and that also doesn't seem to be a good solution. However, a prior work PREFI showed that you can involve the relay or the gateway in the protocol itself and eliminate the communication among the users, but you need the help of a few setup servers. These setup servers help in the setup phase, and then the users can run the protocol. As long as every user trusts at least one of the setup servers, you can guarantee anonymity. In our design, we require that the setup servers do not take part at all after the setup phase is done. And this is a key difference between PREFI and OrgAn, because in PREFI, the setup server still communicates with the relay during the anonymization phase. So let's see in general how these setup servers can help. The setup servers can help the users agree on shared secrets among themselves. We have the local area network, we have the setup servers. Each setup server J splits a value S, where S is publicly known, to multiple values R1J, R2J, R3J, R4J, because there are 4 clients here. That's why 4 values, and shares those values with each of the clients using a secure channel. After the client receives these secret values from each of the setup servers, each client can add them and derive his own secret. What the relay knows is that some of the secrets of all the clients is k times s, where k is the number of servers and s is the publicly known value that is split by each server. But the relay does not know the individual secret values, RI values, for honest clients. Now these clients can run a DCNet protocol with the help of the relay. Let's see how. We have the local area network, we have the setup servers. This is what the relay knows. But wait, didn't I say that once the setup phase is done, we don't need the setup servers anymore? In our design, we use additive key homomorphic PRFs, where f of r1 comma d plus f of r2 comma d equals to f of r1 plus r2 comma d for a tag d. Here d can be the round number. Now, if Jim wants to send a message x, what Jim sends is x plus f of r1 comma d. And rest of the clients, Ryan, Andy, and Pam, they only sends the PRF values. Now what the relay can do is relay can retrieve x by adding all the ciphertext received from all the clients and subtracting f of ks comma d, because the relay knows that sum of all the PRFs equals to sum of f of chaos comma d, because it's an additive key homomorphic PRF, and the relay can retrieve the value x. However, how does any user, for example Pam, know that in a specific round she is not supposed to send a message because someone else is sending a message without knowing who is actually sending a message? How do the users agree on such slots? For that, we use Newton's power sum equation system. Newton's power sum equation system is an identity, so the order of inputs does not matter. You get the same output. And we can use such an equation system to achieve anonymity. Let's see how the relay can receive such an equation system. In our system, every round has n slots, so each user sends exactly one message in every round, and for n messages there are n slots. For every slot, each user I sends the ciphertext CIT, which is xi, where xi is the plain text of the client, raised to the power t plus the PRF value with tag t. Assuming the round number is 0, we are using the slot number as the tag, just for example. And every client then sends n ciphertext for n slots. After receiving n ciphertext from every client, for every slot, the relay can add the corresponding ciphertext from each of the clients to retrieve the value x1 to the power t plus x2 to the power t plus xn to the power t, and that gives the equation corresponding to slot t. So for n slots, the relay gets all the for n equations, and the relay solves those equations to retrieve the values x1 to xn. And since the order of the inputs do not matter, the relay does not know which user sent which value. And voila, we got our protocol. In our protocol, the PRF computation seems to be a huge overhead for the clients. And we reduce the overhead by using an almost chemomorphic PRF based on ring learning with rounding assumption instead of a classical chemomorphic PRF based on DDH assumption. In our protocol, the exponentiation in the classical PRF is replaced by vector dot product. However, this introduces some noise in the PRF function, but as long as the noise is a small value, we can eliminate the noise by multiplying the plain text with a scalar value. The main takeaway from this slide is that we improve the PRF computation time by increasing the size of the keys, because the key is now a vector instead of a scalar. If you look at the PRF function more closely, you see that the hash function does not depend on the key or the plain text of the client. So we can further improve the computation over it by pre-computing the hash values for a tag of up to certain range and store those hash values. But once the hash values are exhausted, the clients need to rerun the setup to reuse the same hash values. And this gives us a storage versus computation trade-off. However, this allows us to speed up further. Now we have the core construction of our protocol. Let's call it OrgAn A. We also introduce a bulk protocol that allows clients to send large IP packets. We also defend against active attacks like equivocation by the relay, disruption by the clients or relay, and all these without compromising anonymity. I encourage you to read the paper for all these details. We have an end-to-end implementation of OrgAn with all the add-ons in Rust, and the implementation is publicly available. And using this implementation, we show that we can support throughput, which allows for audio calls even for 100 client system. If you look at the table, for 50 client system, the throughput is 11 kbps per client and 3 kbps when there are 100 clients in the system. To summarize the takeaways from this talk, we need the requirement of setup phases for key agreement and slot agreement before every round in a DCNet based protocol using a combination of Newton's power sum method and additive chemomorphic PRFs in the client relay server model. We also show a storage versus computation trade-off in chemomorphic PRF, which is a public key primitive, and we show that it is possible to make it really faster. Thank you for your patience, and I will open the forum for questions.